Okay, so these two matrices were not similar because they had different Jordan canonical forms. We just calculated that out. So what I'd like to do on this problem is find all possible Jordan canonical forms for a 7 by 7 matrix that has the same eigenvalue 7 times, I'll call it lambda, and the eigenspace is 4-dimensional, right? So what does the fact that it's 4-dimensional tell you? There are going to be 4 blocks, right? So what I would like to know is what are the possible breakdowns of those sizes of those blocks if there's 4 of them and the whole matrix is 7 by 7? Okay, you got to give me 4 things. So what did you say? 3, 2, 2, 1. What's that at? Wait, that was it. Right.
3, 2, 1.
Okay, I'll take that.
1, 1, 1, 4.
I'm always put the biggest numbers first. So I'll put 4 first.
2, 2, 2, 1.
2, 2, 2, 1. Basically, you're asking for how many ways to get 4 numbers to add up to 7. 4 positive integers to add up to 7.
It's for the largest number.
Well, if you use a 5, and you got to have 3 more numbers here that are each at least a 1, it's going to be too much, right? So the biggest size block you could have would be a 4 by 4 block. So this one here, let's just, while we're thinking about it, let's just write down what it would look like. You'd have one 4 by 4 block, so it would look like that. And then 3 1 by 1 blocks. So that would be the form of the Jordan canonical form for that. On the other hand, for this one, you'd have a 3 by 3 block. And then you'd have a 2 by 2 block. And then you'd have a 1 by 1 and another 1 by 1. My markers are not doing too good here. Let's see. I set down that one that was so good earlier. This is better. Okay. And then the last one would be a 2 by 2 block, another 2 by 2 block, another 2 by 2 block, and then a 1 by 1 block. Okay? Does that make some sense? Let's say that, so there's 3 possible Jordan canonical forms, and you're there. To decide which one is the right Jordan canonical form, I need more information. So I could give you more information. I could tell you something like, so this would just be as a follow-up now. If a minus lambda I squared is not 0, but a minus lambda I cubed is 0, then which one of the 3 possibilities is correct? So if I know that the square power is not 0, but the cube power is 0 of this matrix, then this one here? That's not my answer. Let's think about how the cycles look. So the cycles are, here's V. We have a minus lambda I V, right? Then we have a minus lambda I squared V. And I've said a minus lambda I squared is not 0. So this matrix is not, guys, if you have a matrix that is not 0, then there must be some vector out there that survives that matrix, right? If I give you a matrix, and even if every entry except 1 is 0, if almost all of the entries are 0, but if there's even one entry that's not 0 in the matrix, you will be able to choose V. You will be able to choose a V that survives that matrix. See, the way I like to think about it is, you're not just choosing something here and then just floating it down, hopping it along this cycle and hoping that it lasts a long time. You're gonna think ahead and say, I want to choose something here that will still be alive over here. If it's alive over here, then it must have been alive all along the way because you're going from right to left. So do you agree that since this matrix is not zero, I will be able to choose a V that survives all the way over to here? So doesn't that mean I'm going to have a cycle of length 3?
No.
But can I have a cycle of length 4?
No.
No, because a cycle of length 4 would require a vector to survive a minus lambda I cubed, and nothing will survive a minus lambda I cubed. So which one is the right answer? The first one, second one, or third one? It's got to be this one. Isn't that amazing? You can answer that so quickly, just based on that. Okay, perfect. All right, let's do another example. Let's see. I'm going to come back over here. Okay, so this is number 4. We're going to kind of switch topics a little bit here. I'm going to define T to go from P3 of R to P2 of R via T of P of X is equal to P prime of X. So take a derivative of the polynomial. And then I'm going to define U to go from P2 of R back up to P3 of R via U of P of X is equal to X plus 1 times P of X. Okay? And then I'm going to write down a couple of bases for these vector spaces. So I'm going to let beta, which is going to be 1 plus x, comma, x plus x squared, comma, x squared plus x cubed, comma, 1 minus x cubed, be a basis for P3 of R. By the way, if I say something like that, then you can assume it is a basis. You don't have to, that's not really the focus of this exam anyway. You can just take for free that that is a basis. And then I'm going to make another basis, gamma, which is going to be 1 plus x, and 1 plus x squared. So those three things there. And I'm going to let that be a basis for P2 of R. That's the basis for P2 of R. Yeah, Davey?
This is under review.
Yeah, this is number 1.
Oh, it's in my review packet?
Yeah.
Oh, so then we don't need to do it, right? Or should we do it anyway?
Right.
Do you want me to keep going? I didn't realize that. This is actually coming off of my review session problems. I must have.
Maybe
I get
ask the
confused.
different section,
Number
but
one.
all of that's on there.
All of this is exactly the same.
Yeah.
Yeah.
So what was the question that I asked?
There were like
Find,
4 parts.
there was like 4 parts. One was find U composed of T.
Okay.
So we can find the
There's
You
one
know
matrix
what?
representation of T and the matrix representation of U.
Okay.
And then
So
there's
I've
a
already
review and
basically done
alpha
this.
too, right?
Hmm.
What other one? Was it this one?
Okay. Can I see? Do you have the review packet, Joseph?
Yep.
Can I look at it? Thanks. I meant to bring this up here and then I didn't, so that's not really what I want. I don't necessarily need to go over that then. Let me make sure that I'm not asking too many questions that are the same. These are some good problems, aren't they? In the review packet, I think. Maybe that's why I decided to do it. Okay, let me change the problem then. All of that for nothing. I'm sorry. But this will save us some time. Need to actually go through that one. Okay, let's do let's do this problem instead. So I'm still on number 4 now. Is that right?
Yeah.
Yeah, number 4. Okay, so let's take a positive integer n, and I'm going to define t to go from Pn of r over to Pn of r via t of f equals the integral from 0 to x of f of t dt minus 1 over n plus 1 times x plus 1 times f. Okay, I think this is new. This doesn't look familiar to anybody, does it?
No.
Okay, great. Try this as a new example. Okay, and then I'm going to let beta be equal to 1x, x squared, da 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 da, up to x to the n. Okay? And then the question that we're going to ask is, find the matrix representation of t with respect to beta. Okay, let's try that. So, Joseph, I'm going to hang on to this.
By all means.
Okay, thank you. Okay, so we're practicing kind of the same stuff that other example was going to practice. So to find this matrix representation, what do we need to do? Transform each of these basis vectors, get an answer, and then take the results and write them again in terms of this basis. Okay? So let's see if we can do that. Hopefully I've given myself enough room here. So we need to find t of 1, right? So let's start off kind of careful with that. T of 1, I have to integrate from 0 to x of dt. Well, that just gives me t evaluated from 0 to x, which is just x, right? So I get x minus, and then I have this part, 1 over n plus 1 times x plus 1. So that's my answer. Now I have to rewrite that answer in terms of as a linear combination of my basis again. So what's the constant term over here? 1 over n plus 1? Not 1 over n plus 1. Constant term. Negative 1 over n plus 1. Okay? And then what is the x coefficient?
One minus.
1 minus 1 over n plus 1. Okay? Okay. So if you wanted, you could rewrite that. It's negative 1 over n plus 1 plus, if I make a common denominator of n plus 1 here, I'll end up with n over n plus 1 times x. Right? Okay. So that's that. I'm going to start, I need to find a spot to start writing out my matrix. What's the size of this matrix going to be, by the way? N by n? I don't think so. Not n by n. N plus 1 by n plus 1. Guys, make sure you have your dimensions straight. This is n plus 1 dimensional. This is n plus 1 dimensional. So let me just give myself a lot of room over here. T with respect to beta. This is a large n plus 1 by n plus 1 matrix. But I now know the first column of it. I have a negative 1 over n plus 1. And I have an n over n plus 1. And then everything else below that is going to be zeros. Okay so far? Okay. Let's calculate t of x. So my function is x, so I'm integrating basically t dt. When I integrate t dt, I get 1/2 t squared, which I now evaluate from 0 to x, so I'm going to get 1/2 of x squared. So far so good? minus 1 over n plus 1 times the quantity x plus 1 times x. This time, there is no constant term, because there's no constant term here, and there's an x there, so there's no constant term. What is my x coefficient? Just the x coefficient. Just the x coefficient. There's no 1/2. 1/2 it goes with x squared. What goes with just with x?
Negative 1 over.
Negative 1 over n plus 1, right? Okay. And then what goes with x squared then? 1/2 minus 1 over n plus 1. Okay. And that's it. And I can write down the second column of the matrix. It's going to be 0. Then it's going to be negative 1 over n plus 1. And then it's going to be, I'm just going to write this as 1/2 minus 1 over n plus 1. I'm not going to simplify it. Just going to leave it like that. And then everything else below that is still 0. Okay? You guys with me? Let's do the third column, and then we'll jump to the last column. We'll kind of get the idea here. So the third column would be t of x squared. Okay, let's try and do this a little more quickly. What will t of x squared be? No negative. I'm not starting with a negative. Just the first part. What's it start off? 1/3 of x cubed minus 1 over n plus 1 times x plus 1 times x squared, right? And I need to rewrite this. Now, is there a constant term here? No. Is there an x term here? No. What is the x squared coefficient?
Negative 1 over n plus 1.
Perfect. Negative 1 over n plus 1. Good. And then what is the x cubed coefficient?
1/3 minus 1 over n plus 1.
Now we're getting it. Exactly. So it looks just like that. So over here, the third column, we have 0, we have 0, we have negative 1 over n plus 1 again. And then we have 1/3 minus 1 over n plus 1. And then all zeros below that. Okay, so we're kind of getting the idea. Let's go to the very, very last term just to see if anything weird happens at the end of this process. T of x to the n, so that's my last basis vector in beta. What is t of x to the n going to be? One over n plus 1 times x to the n plus 1, right? Just anti-differentiate that. Okay, and then minus 1 over n plus 1 times x plus 1 times x to the n, right? What happens with that when you simplify it? First of all, can we have a polynomial of degree n plus 1 here?
Yes.
We can? What's the highest power of x that we should ever see? X to the n, right? So do we have a problem here? This looks like n plus 1 power. It's going to cancel over here, right? See, you have a minus 1 over n plus 1, x to the n plus 1, but it exactly cancels. The only thing left after you simplify this, actually, is negative 1 over n plus 1 times x to the n. So this one actually cancels, whereas the earlier terms did not have a cancellation like that. So this last column is actually all zeros all the way down to here, and I get negative 1 over n plus 1. Does that look okay? So I think that's what I got. Okay, so we have that matrix. For what it's worth, we have that matrix right there. So I now have a few more questions about this matrix. Actually, I'm going to start with, so I have some follow-up questions. Okay, so let me ask you a question. Is T invertible? Is T invertible? question about T often is the same concept as answering a question about its matrix representation. So here's its matrix representation. So instead of asking, is T invertible, I could ask, is this invertible? And if I give you a matrix, how do you normally check if a matrix is invertible? The determinant, right. Do we have a chance of finding the determinant here? It's actually very simple. Think about it. Look at the form of the matrix. Oh, no. Very bad drawing there. It's lower triangular. It's lower triangular. Everything above the main diagonal. See, the main diagonal is all of these negative 1 over n plus 1s, right? Would you agree that the determinant of this matrix, and therefore the determinant of T, is just negative 1 over n plus 1, n plus 1 times? Because what's your main whenever you have a triangular matrix, right, the determinant is just the product of the diagonal numbers. Well, this is a triangular matrix, and there are my diagonal numbers all the way down. It's just negative 1 over n plus 1 a whole bunch of times. Is this equal to 0? Nope, this part's not 0, and this is a power of that, so this is not 0. So what's the answer to my question over here? Yes, it is invertible. Looks good to me. Okay, let's ask another question. Is T diagonalizable? Okay. Is it diagonalizable? Let me propose an answer. Oh, well, first of all, to decide if it's diagonalizable, the first thing I have to do is find the eigenvalues. What are the eigenvalues here? So my lambdas are all just negative 1 over n plus 1, negative 1 over n plus 1, da 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 da. Whenever you have a triangular matrix, the eigenvalues are just on the diagonal, right? So, how do you like this reasoning? We have a repeated eigenvalue, therefore it's not diagonalizable. It's not good, right? You don't want to say that. If there were no repeats, then we could definitely say, yes, it is diagonalizable. But if there are repeats, we have to do further work to make up our mind, right? We have to do further calculation, further analysis before we're going to be able to say whether it's diagonalizable or not. So what do you guys think? So how do we do this? Well, we have to subtract the lambda from the diagonal and take the null space of whatever's left. Well, after I've done that, I'm going to basically get the same matrix again, but with zeros on the main diagonal. And then I'm getting numbers here, and I'm going to, let's see, then here I'm going to get 0, and then a number, and then a 0. All these are zeros, and then 0, 0. I'm going to get numbers below the main diagonal, right? And then down here on the very end, I'm just going to get all zeros, it looks like. Oh no, I'm sorry. There's a number here and there's a number here, right? So there will still be a number right there. So actually, I more or less have told you now how the pivots are going to look, right? How many free variables do I seem to come up with? Only one, right? There's only one free variable, which corresponds to the last column. In order for this matrix to be diagonalizable, this eigenvalue would have to pull its weight. Its multiplicity is n plus 1. This lambda shows up n plus 1 times as an eigenvalue. But then when I ask what's the dimension of the eigenspace, you guys are telling me it's only 1. There's only one pivot there, right? So this eigenvalue does not pull its weight, so the answer here is no. By the way, folks, there is no connection between being diagonalizable and being invertible. You can have one without the other in both directions. And there's a group work that I gave you that sort of asks you to give examples of that. But here's another example. This is invertible, but not diagonalizable. Does this make sense? Okay. So let me just ask you this. Would we be able to write down the Jordan canonical form of this matrix? This is just a follow-up. It would also be an n plus 1 by n plus 1 matrix. Could we actually write down, would we be able to write down what it actually is? How many blocks would there be? I'm sorry, I didn't hear what you said. How many blocks? One block. You have to know that. The sizes of the blocks are the length of the cycles. The number of blocks is just that. So there's only one block, guys. And how do the blocks look? Well, the eigenvalues, which we know, the eigenvalues go along the main diagonal. And if there's only one block, then that means that there are ones all the way along the super diagonal and zeros everywhere else. So there's the Jordan canonical form of this matrix representation. Are we doing all right? Okay. By the way, I can't remember if I think I told my other class this. I'm not sure if I told you guys about this. Does anybody happen to, I'm going to call this a fun fact. This may be, actually fun facts, I'm going to give you two of them. This may be something, I can't remember if I've done this in class or not. Does anybody know a formula for the determinant of a matrix in terms of its eigenvalues? So if I have a matrix that's 3 by 3 and its eigenvalues are 2, 5, and 6. Anybody happen to know what the determinant of the matrix is? Actually, it's very simple. What it is it's just the product of the eigenvalues. You just multiply all the lambdas together. Has anybody seen that before? Maybe I didn't go over that with you guys. I mean, the reason for that is actually pretty simple. The idea is that to find the eigenvalues, you are looking at this characteristic equation. Let me use a T here, actually. So the eigenvalues are the solutions of this equation. Let's suppose that my eigenvalues are these n lambdas right here. Then that means each one of these n lambdas has to solve this equation. So when basically you're going to set this equal to 0 to find your lambdas. And what we're saying though, see, every time you find a lambda value, then you're actually finding a root of the polynomial. So there is one root that would have to have the form of lambda 1 minus t. And there's another root that would have the form lambda 2 minus t. And so on. In other words, this characteristic polynomial actually must factor. And the roots that correspond to those factors are precisely the lambdas that you have the eigenvalues of the matrix. So you have to have that equation right there. And if you imagine multiplying that whole thing out. Well, actually, don't even do that. Even easier than that. Just plug in t equals 0 on both sides. Plug in t equals 0. Both sides. See it? There it is. This is actually pretty simple to explain that the eigenvalue